Hello friends, it's Kalpesh Jani and I'm very glad to address you people via this medium of video presentation. So friends, let us take a recap of the things that we have studied in the first part. We started with the introduction of the thermodynamic potential, then we went to give the historical information regarding the thermodynamic potential terms. Then we proceeded to have the gross definition of the thermodynamic potential, various type of the thermodynamic potential. We had the overview of the various type of thermodynamic potentials. Then we proceeded to work out the first and very fundamental thermodynamic potential, which is nothing but the internal energy of the given thermodynamic system. Then we had the overview of what does it mean, the internal energy of the thermodynamic system. We had the overview of that. Then we worked out the first part of the internal energy of the given thermodynamic system using some computer animation. This part is the potential energy associated with the given thermodynamic system. So this much we have done in the first part. Now in the second part, as you know, that this internal energy of the given thermodynamic system is made of two parts. The first part is the potential term that we have worked out in the first part, and the second part is the energy retained with the system by the supplement of heat from outside. So we shall start with that part. We shall continue the computer animation that we started in the first part and work out the energy retained with the system, thermodynamic system, by the supplement of heat from outside. So now we shall uh, actually calculate the other part, which is nothing but the energy retained with the system when we supply heat from outside. So how to calculate this energy which is retained with the system with the heat supplement? So we have this system in which the gas molecules are constantly moving with at a given temperature and pressure. Now there must be some amount of heat which is possessed by the system right now at a given temperature and pressure, and also uh, the value of entropy and volume of the given system. Now let us try to find out how much energy actually is retained by the system when we supply heat from outside. Then we shall calculate what is the change in the internal energy after the supplement of heat from outside, and from that we shall work out the energy which is retained, the increase in the energy which is retained with the system with the supplement of heat from outside. So let us heat this system up a little bit, and then we shall see how much there is increase in the internal energy, or the second part of the internal energy. So in doing so, we are doing this at a constant temperature and pressure right now. So when we heat up the system at a given temperature and pressure such that the temperature and the pressure of the system does not change, then so let us suppose that dq amount of heat is actually supplemented to this system from outside. And what is the outcome of this supplement of heat from outside? Obviously we can expect that there would be an increase in the motion of the molecules of the gas. As you can see here that the overall motion of the molecules of the gas have been increased. Now what would be the consequence of this increased motion of the molecule? So that will do two things. First, overall kinetic energy of all the molecules will be increased, so the temperature of the system would tend to increase. Secondly, because of this more kinetic energy, they would tend to collide with each other more frequently, and so the randomness in their motion will also tend to increase. So the entropy of the system would also tend to increase with the supplement of heat from outside. Now we have to keep temperature and the pressure constant during the process. Now we shall have to make some arrangement for that, and we have to do the process very slowly so that the temperature and the pressure do not change during the process. Now what arrangement we shall do in this? We shall put one piston in the system so that the piston can move with the supplement of heat, and the system can do some mechanical work with the supplement of the heat from outside. So we can say that the amount of heat that is poured into the system, that will be expended partly in increasing the entropy of the system, and partly it would be expended in doing some mechanical work. Now the piston can move and it can do mechanical work. So let us make an arrangement first and see then what would happen to the system. So here we have made an arrangement of piston, and we can see that with the supplement of amount dq from outside, then the system would partly have the increased value of entropy, and partly it would do mechanical work. So piston will move and the system would do some mechanical work, and that mechanical work can be denoted as dW. It can be given by P into dV, where P is the constant pressure that we have kept during the process, and dV is the amount of volume which has been increased and the mechanical work has been done by the system. So we say that dq amount of heat has been expended in partly increasing the entropy of the system and partly doing mechanical work. Now let us give it with the equation. uh, we can say dq amount of dq amount of heat that we have supplied from outside has been expended in partly in the overall energy, uh, which we can say that the heat content of the system, and partly it has been expended in doing mechanical work. So now we have to find out the first portion, which is du, the heat which is retained with the system after the supplement of the dq amount of heat. So there would be increase in the heat content of the system after the supplement of dq amount of heat, and that increase in the heat content of the system would be given as the increase of the internal energy of the given system. So it is a second part of the overall internal energy of the given system. So let us write down the equation in terms of du, the change in the internal energy of the given system. So if you have to write down in terms of the change in the internal energy of the given system during this process, we can write it like du is equal to dq minus dw, and we have seen that dq is nothing but T into ds. We have kept temperature constant, and there is a change only in the entropy of the system, minus the work that is done by the system is P into dV. So du, the change in the internal energy of this system while uh, supplementing dq amount of heat from outside, is TdS minus PdV. In the previous slide that when we supplemented dq amount of heat to the system, in the starting there were some value of temperature, pressure, entropy and volume of the system, and then we kept the temperature and pressure constant. We made such an arrangement during the infinitesimally small supplement of heat from outside such that the temperature and the pressure of the system do not change. We made an arrangement of the piston which can move with the supplement of heat from outside, and we have seen that with the uh, supplement of the dq amount of heat from outside, there is an increase of the entropy, overall entropy of the system, as well as there would be increase in the volume of the system. The piston moves a little bit and some mechanical work done by the system. And we have also seen the amount of the energy, increase in the energy retained with the system, that to which we call the increase in the internal energy of the given system, plus some amount of work which has been done. So the total increase in the energy retained with the system, which is nothing but the uh, increase in the internal energy part of the system, can be given as TdS minus PdV. Now let us extend this idea and say that suppose we at starting we shall have some value of pressure, volume, temperature and entropy, and then we start giving a small dq amount of heat to the system, keeping temperature and pressure constant, and then we repeat this process for n number of times, and all the time we shall see what amount of entropy and the volume which is increased after the process. So we shall have to uh, integration of these two terms, TdS minus PdV, over all duration of this process, and integrate all the change in the entropy and the volume of the given system during the process. So the overall increase of the internal energy of the system can be given as the summation, or sorry, integration of these two terms. Now we can say if the starting point is the point where there was no internal energy due to the heat content of the system, then the overall value of the internal energy, the second part of the internal energy, is just the integration of these two terms over whole period of process. So this is the way we define the second part of the internal energy of the given system. Now, during this process, we have one thing we have kept in our mind, that there is no change in the potential value of the given thermodynamic system. So if we have to represent the overall value of the internal energy of the given system, we shall have to add up these two terms. One, the energy retained with the system in the form of the integration of TdS minus PdV, plus the potential part which has already been there with the thermodynamic system. So we shall have to show the overall internal energy of the given system, as we shall see in the next slide. As it is shown in this slide, that the overall internal energy of the given thermodynamic system can be represented by this equation. It can be represented as the integration of this two term TdS minus PdV plus some constant potential term, because we have kept in our mind that there is no change in the potential energy during the process. But if we take the fact that there is a change of the potential energy during the process, then we shall have to take that into account. Now, how can a potential energy be changed during the process? There are two ways. First, there is a chemical reaction taking place during the process, and the the structure of the molecule itself changes during the process. We shall not take that part at this point, because it is little complicated to uh, account for that change in the potential energy, but we shall take the part in which the potential term can be changed because of the inlet of the gas molecules from outside during the process, or outlet of the gas molecules uh, from the system during the process. So if we allow the gas to uh, if we allow other gas molecules to come inside the system during the process, or we allow the gas molecules to go out from the system during the process, then there is a change in the total number of molecules during the process, and because of that change in the total number of molecules, the total potential term will also change. So in that case, we have to take the integration of all the small changes of the number of molecules during the system. So the total amount of change of the potential energy along with the heat, the energy which is retained with the system in the form of heat content. So the total internal energy in that case would be given as the integration of all these three terms, TdS minus PdV, plus this summation where the number of molecules are subject to change during the process. So this is the final equation by which we can show the internal energy potential of the given system.